University. And the title is Reconstructing Reality from Physical World to Virtual Environments. Let's welcome Professor Lin. Let's welcome. Okay.
Can you hear me?
Yes, we can hear you now.
Okay.
Okay.
I'm going to be sharing, hold on a second. I'm going to be sharing my screen. I hope you can see it.
No, we can't see your slides.
Okay. It says only one participant can share. I needed permission to share. I don't think I can. Hold on a second, let me see. For whatever reason, I'm not able to share the screen.
See you. No.
Can you give me the ability to share?
Yes.
Hello, can you?
Yes.
Can you hear me?
Yes, we can hear you.
I'm not able to share. I think you need to allow me to share. Okay, hold on a second.
Okay, yeah, we can see your slides.
All right, can you see it?
Yes, it's okay now. Now we can see your slides now.
Yes, can you see it?
Yes, we can see it.
Can you see it on your side? Can you see the slides?
Yes, we can see it.
Okay, great, thank you. All right, so I sort of modified the title a little bit. I think the title here is more reflected of what we are really doing. And today I'm going to talk a bit about reconstructing reality, which is creating a digital twin for the metaverse. This is a cumulative work and research with my collaborator and students over the years. So network VR, AR, and MR, collectively called the extended reality, is what many people think about as the metaverse. And the focus of this work is really to talk about how do we bring the physical world and bring the physical world into the metaverse, this network of extended reality that we are increasingly living every day. And this general area of extended reality, which can including AR, VR, and mixed reality, which transcend the digital and the real world, is one of the most disruptive technologies for the next decade, according to many of the reports and so on. It's so big a deal that Facebook changed its name to Meta. And part of the reason is that the application of metaverse can be limitless. So what's our vision regarding the metaverse? Well, what we are really interested, I think, in the future, in particularly for people who are working in computing in general, computer science, electrical engineers, mathematics, machine learning, AI, what we are all interested in doing in many ways is creating the ultimate metaverse. And that is to try to capture and reconstruct the dynamic real world. Even in machine learning, in AI today, people are talking about the world model. What's the world model? It's really a representation of the dynamic world that we live in. And what we want to do is bring that physical world, the real world, into this shared metaverse that we all live in today, which transcend the boundary between the real and the virtual, the digital and the physical, and enable the seamless interaction in the metaverse. And also, the most important thing is to create what I think, generally speaking, we would think about as impossible. That will including the virtual playground for the students, for the scientists, for the engineers to explore, to test, to design, to validate, and to prototype, which I call the Meta Lab. There has been a lot of work on this idea of a reconstruction. It started from a long time ago, way back in geometry and in computer graphics, where we have done an extensive amount of research on geometric reconstructions. Here are just some of the examples. We have extended this concept from geometry reconstruction to scene reconstruction. And here are just sort of some of the more recent work that are published in computer graphics and also in computer vision by colleagues and friends of mine. But then we go way beyond geometry and scene reconstruction. We are also been looking at, image and video reconstructions across both computer vision and computer graphics that really are looking at some of these really challenging problems. And most recent work, we have moving into this photorealistic reconstruction, talking about neural radiance fields, talking about all kind of Gaussian, all kind of neural representation. And more recently, we also have this volumetric image-based representations, including Gaussian splat and various neural representation that has been proposed by both researchers in computer vision and computer graphics. But just be able to reconstruct a world that look photorealistic, it's actually not sufficient. We also need to think about what's in the real world. If the world is static, it's not all that interesting. And the reason the world is interesting is because we move, we live, we work with it, and we're working there. So motion is an integral part of all these universe, whether it's real or virtual, that we live in. And motion is important to capture. It's important for us to resynthesize and control the motion of digital character, like some of the example here. So over the decades, many different researcher colleagues and friends of mine in computer animation and physics-based simulation has also been working on reconstructing motions and how to control these simulated motion. And more recently, we have also been seeing the tremendous amount of interest in creating digital avatars, like these you see here. We are not interested just creating the body representations, the shape and the geometry, but also how they move. And we are seeing increasingly more the capturing of the motion, the animation of these avatars across all different kind of menus. So one of our work that we have been working on is basically what we call this shape-aware human poses and body reconstruction using multi-view images. And this is also one of the more recent examples. Now, we have also been looking at reconstructions of cloth and fabric and garments. And part of the reason that we're interested in doing this is because most of the characters and avatar all wear clothing. But also partly it's a personal fashion, and as a personal, it's a personal aspiration that fashion is really important because it represents us as a person. And there's a tremendous interest in computer graphics over the last decade or so, where there has been increasing interest on how do you design clothing. And part of the reason is shopping online really required this kind of technology so that we can find clothing that will fit us. Clothing, it's not just what we wear, it's also a statement about us as an individual. So through all these examples, I hope that you get a sense that the data that we capture the physical world with can come in all different fashion and different way. For example, 2D images, 3D geometry models, undimensional motion capture data, audio, video, medical informations, sensor data that capture the environment monitoring and measurements, and other documents and social media and webs. The challenges is the diversity of the data representation and their format. Also, their dimensionality. Could it be 2D, 3D, or n-dimensional? And it could be text, numbers, images, audio, video, or abstract concept. It could be geometry, physics, appearance, or behaviors, like human behaviors. And also functional representations of objects, tools, for example. And then what's important that not many people are talking about, but it is increasingly becoming obvious, is the volume of data that we have to deal with. And also the noises and uncertainty and the incompleteness of the data that we capture. All these are challenges arising from, capturing the data. And sometimes there is not enough data. We have to also simulate it or synthesize it for training, neural network. So these are some of the most recent challenges. And the question here is, how do we address them? So some of the work that we have looked at more recently is this audio-visual reconstruction. And here is another example where capturing the real world is really, really critical for, robots. But this is a perfect example that we don't have actually enough information. If we just use camera capture, there is inadequate information. For examples, some of the robots are not very good at capturing windows because it's transparent. So in this case, audio can help bridging that gap. So we are also looking at many different kind of modality that can be used to reconstruct and represent the world, audio, visual, and that can complement each other. Another area which increasingly will be of importance is the smart cities. For examples, we have a large city out there where people are increasingly living in urban environment. 70% of worlds today are living in the cities. So how do we capture people moving around in the real world? Most of them in urban environment where they are walking or moving around, and doing all kind, like mobility is also becoming an increasingly important problem for us to address from these capture data, whether it's pedestrian walking on the street, car driving on the street, or just highways and of all type of different transportation means and so on. So we have also been looking at simulation of a large crowd, which include data-driven simulation. And the basic idea here is to use data to simulate crowd, use video data to simulate crowd movement. And so the trajectory can be extracted automatically from a single videos. Then we can reconstruct how they move around, for example, and then start simulating a different scenario, such as during the holiday, where we can use the information extracted from video to reconstruct the world, like a train station where you can simulate how people move and so on. And so we can add more virtual pedestrians to the simulations. We can create the what if scenario, like what happened if we add a Christmas tree? How will people move differently? Well, what happens if there is unexpected events like a fire? How would that change your environment, and how would that change how people move? And so, taking the real world video was just only the starting point. But we are now using that real world video to initialize a simulation, which we call it basically a data-driven simulation. We are able to extract the information, the pedestrian, the crowd dynamics directly from the video, use that as the input. And then we can create this what if scenario, create all kind of events to see how people might move, how their behavior change, how their dynamics and how their interaction would change among them. And this can go on and creating a really nice loop where we are able to mix real and synthetic environment together and asking all kind of what if question. So here is an example of showing that. So this is the video I showed earlier for the train station, where we have people moving around and the trajectory will be extracted, as you could see on the right-hand side. If we just play them, these trajectory would look very jittery. But however, once we incorporate a simulation in there, we can now automatically smooth out the trajectory. So the extracted information is smooth by using a motion model, and we are able to resynthesize and recreate, trajectory that would look much more photorealistic. But even better yet, we can now change the scenario, add different elements, and start asking what if question. What would it be like if it's a holiday, when we have statue, when we have Christmas tree? So here's another example where we actually have other YouTube videos that we downloaded, and we were able to track these pedestrians crossing the street. Then once we extract the information, we were able to recreate the same scenario in a virtual world, where we can now simulate how people crossing the street, initialized by the video. But we can also ask the what if question. What if there was a fire? How will people react? You can give these people different personality based on the way they walk, and then you can simulate these different kind of scenario. This kind of idea is not just limited to human and pedestrian. We can also bring it to the traffic world. And why do we care about traffic? Well, first of all, any kind of urban city, as I already mentioned, 70% of the world's population live in an urban environment. And if you're living in, no matter where you live, traffic is an integral part of our daily life as we move from one place in the city to another place. Let's say we get up in the morning, go to work. So you have to move, and transportation is an integral part of that. Traffic is an integral part of that. So what we want to do is be able to capture the traffic data and reconstruct the traffic flow so we can predict. There has been a lot of work that already have done on these data-driven traffic prediction. So reconstructing the traffic is really a very important problem. Now, once we have the reconstructed traffic, we can do route planning. It can add realism to virtual Earth, but also it can help doing city planning. But what is another really, really important aspect is that the reconstructed traffic can also be used to train autonomous car or autonomous vehicle, for self-driving cars to learn how to navigate and interact. And so this is really a very integral part of the future as we move into a world with autonomous system. Now, one of the problem, I'm sorry, I just want to just show you one of the videos. This is based on our reconstruction of the traffic. So what we have here is data that was just in-road sensor data that we were able to capture, and then we were able to use that captured in-road sensor data, which are just digital information, be able to reconstruct and show you how this 3D world would look like with the reconstructed traffic. So this is what I mean by reconstructed traffic. We call it virtualized traffic. So we have taken an abstract reading of the traffic using the in-road sensor data and convert them to a 3D representation, so you can actually see what the traffic looked like from a different angle. On the lower hand side was the driver view. On the top view was basically a top-down view. Now, once we can reconstruct the traffic, we can also use simulation to analyze, accidental scenarios. Why do we do that? Well, part of the reason is all the current autonomous drivings are being trained by using safe driving data. What is difficult to capture is unsafe, pre-crash accidental data. And without those data, the vehicle may not know how to react in these different scenarios. So we actually have proposed using simulation to capture these very difficult scenarios to capture in the real world. And obviously it is based on, reconstructed physical environment and reconstruct the traffic flow, and then couple together with a vehicle simulation. And this is just a show you why it is useful and why it is powerful. So how do we do it? Well, we run the traffic simulation, so you have the autonomous vehicle driving on the road. Then we purposely put poles and other obstacles in a row, and we have the car literally crashing into it. We can do this multiple times. We can get multiple trajectory. We can analyze the time of crash and how the obstacle can be avoided. Well, so once the vehicle learn through the simulated crash, it will know how to navigate around the obstacle. So the original driving simulator will crash into the pole if it doesn't learn from it. But with ours, after analyzing a trajectory, it's able to navigate around. So these are just sort of a few different scenarios indicating how the effective learning you get from basically these crash simulation scenarios. Now, what's important is that this doesn't just work on the pole, but you can also work on the road, other kind of road obstacles, also different color, and you can see there is actually a difference using this kind of simulated crash scenarios to teach autonomous vehicle how to drive more safely. Now, accidents scenario is not only one. The other scenario is different kind of weather condition. And this is, in fact, one of the most challenging conditions right now for people working in autonomous driving is how do you learn to drive in different weather? And then what's even more important is many of the sensors don't work very well under different weather conditions, whether it's raining, whether it's fall, whether it's ice. So by simulating these weather conditions, it can help the autonomous vehicle how to drive better. We also have simulated all kinds of
Following these slides will be
intersection
examples from the
accident.
accident simulator, along with trajectory prediction results from transfer learning.
And the goal here is really to teach autonomous vehicle how to drive and avoid accidents after a few simulated accidents. So that's the basic
Following
idea.
these slides.
Now, all these examples I just mentioned so far, whether it's pedestrian, whether it's car, vehicle, and eventually transfer to traffic to teach autonomous vehicle how to drive better, or self-driving car how to drive more safely. These are just a few examples. They are all part of the bigger system, which we call the multi-agent systems. And I want to say that we have also worked on other multi-agent systems, such as insects and animals. And these are also important because, insects, it's everywhere. And it also, we can simulate butterflies and bees and help, predicting agriculture, harvesting. We can also simulate other kind of a natural phenomenon and all kind of animal movements. And this is also important for various agriculture and environmental preservation application. And so, what I just have shown you here is that the reconstructions of the world, it's not just limited to geometry, but in the scene, but also extended to a much larger picture of crowds and traffic, multi-agent systems with lots of application. And I show a very simple application of simulated accident scenarios and use those simulated accident scenario through this reconstructed crowd and traffic for training autonomous vehicle. And this is going to be an increasingly important part of our future, where we are going to be designing using AI and machine learning to design and create more autonomous system. It doesn't have to be self-driving car. It could be drone. It could be aircraft, trains, and public transit, and so on. So the possibility there is immense. The other area, other than multi-agent system, that we have been thinking about is simulating soft object like clothes. And this is really, inspired by some of the earlier work that we have done on basically reconstructing garment. And it's already kind of shown earlier that we are very interested, and there has been a tremendous amount of work that have been recreating avatar, 3D avatar. And all these 3D avatar and digital representation of a human, digital human, all wear clothes. And so the question there is, how do we simulate clothes? How do we recapture clothes? How do we recreate clothes? How do we animate clothes? And this is not just for e-commerce. This can also be used to train the household robot, like this example right here, simulated and for robot folding the clothes, and this is a real robot designed to do household chore. That the work that has been done at Berkeley. So for us, we have been looking at how do we capture the real world clothing directly from a single view images. That's where our starting point, but we move on to videos. So to give you some idea what the work that we have done in this area is the following. We assume that we have a single view photograph, but we also know there are thousands and thousands of body that has been captured through our research labs around the world, either in Europe or in Asia. There is also a huge, large body of garment database for all type of basic garments. So given these information on the database of a human body and clothing, we could take any photograph and then be able to automatically, using statistical inferencing and parameterization and learning-based approach, to figure out what the body will be. So we can reconstruct the body easily by using parameterized body representation. We could also look at a photograph, and then we can parse the images so that we know what's top and what's a skirt. And then the next thing that we needed, so then we can reconstruct the geometry of the garment that way. And we already have a database. And again, we can use a parameterized representation for garment as well. But there are things that are very difficult to infer, which is very important for most people who buy garments, who buy clothes online. They always say, well, I can feel the material. So one of the things that we have looked at is it possible to directly infer the material from a photograph or from the video? And I can share with you that our experience told us that it is possible. So how do we do this? Well, we basically look at the parse garments, the top or the bottom, and the estimated body. From these parse garments, we're able to recreate a 3D representation because there are a large database of the garment where we can infer. And then we can use and recreate an estimated representation. Then we would drape on this estimated body. And because there is a large database of these garments, we even know how the sewing pattern will look like. For example, this is some of the sewing pattern for the top. And we can actually create 3D representation of simulated clothes and drape it on the body. The challenge was, what's the material? We started with some sort of initial guess. We simulate the 3D clothing on the body. And then we take a look at the simulated clothes against the original photographs. We look at where the folds and the wrinkles are. And based on those information, we adjust the simulation and adjust the garment fabric material property. And we keep doing this in an iterative loop where we do a joint material and a post optimization and a parameter estimation of the fabric until they look right. And this is basically guided by the density of the wrinkle. And the reason that we did this is the density of the wrinkle give us some estimation about how good our parameter estimation for the fabric material will be. So that's the basic idea. So this video actually show you some of the example that we have worked on. On the left is the original images. In the middle is the estimated and recovered body and the garment. So you can see the body in blue and the recovered garments in different shapes and color. And once we are able to reconstruct these garments, sorry, I'm not quite sure what's going on here. So once we are able to reconstruct the garment, not only we can we have the geometry, we can also animate the body because these bodies are articulated body with a proper dimension. So, you can also see how the garment will move on the body as the body turns and twists. And we can also transfer the garment from one model and to a different poses. You can also view them from a different viewing angles. Sorry, this is I'm getting a jumping around. All right, so that was some of our earlier work, but we could also do the same directly from videos. And so the basic idea here is we basically create this neural network where we use a combination of CNN, which is a standard convolution neural network, with LSTM, which basically it's a version of neural network that will have the memory. And we use CNN to extract the image features. And we use LSTM to basically track how that feature moves over time. And from this, we can extract the material type directly from the videos. And just to kind of give you some idea what was actually going on, we actually, in order to generate the large amount of data, we did not have a large amount of data. We were using the data taken directly from MIT that captured. It was a very small amount of data. So in order to address the deficiency in the data, we actually simulate a large amount of data that you just saw. And we use that to actually train the neural network. It turned out to be a combination of the real and synthetic data was enough to actually teach a neural network to classify different material. So you could see on the left, these are different type of fabric, and on the right, it's the simulated and the predicted motion. So I'm going to show you just really quickly again. So these are on the left, it's all different video that was captured by MIT lab. And we were able to extract and recreate the material property and recreate a motion, as you could see the simulated on the right. And then using this technique, we are able to transfer the material property on the right, on the left video to the simulated garment on the right, on this animated body. Okay, and if we have a different material from the left, you will see a different flow of the skirt. So the stiffer the material, the stiffer the skirt will be. And that is the basic idea that we are hoping that this will do, as we are able to capture the real world property and give it to a synthetic or the virtual world, like the dresses or the garment. And here is other much more recent work that was just published a couple years ago at ECCV, where we actually recover the material, but not just the material, but also the geometry and the garment shape directly from the videos. So you could see we actually created this garment of four different garment of two different material. The blue material and the white material are different. The blue material is much stiffer, and the white material is softer. And we have stitched together the dresses so that you can really see very clearly how they wrinkle differently. The material does affect how the clothes folds and how they drape. So again, we use the simulated data to actually train the neural network. So that part of the reason is we can simulate a large number of different clothes, different body shape, and also different postures. So the neural network is able to use simulated data to capture all kind of data that would otherwise impossible to capture. And then once we have this simulated data, we are able to recover both the fabric material as well as the garment. And here's a perfect example where we have a simulated video for training, and then the recovered material being shown on a different digital body on the right. And you can literally see the difference of soft silk. And this is a much, a medium cotton, a little bit stiffer. The simulated video on the right, on the left, and the recovered material being cloned onto the digital avatar on the right. So this is already stiffer than the silk. Here is a really, really stiff polyester. And you could see the materials are very different from the previous one. And you can also see that it looked very different on the clone material or the simulated dress. Now, how well does it work? Well, it works actually really well on the real world video. So this is scenarios where we actually have one of my colleagues at Amazon. We capture his body moving around, and directly we take that videos of him moving around. We were able to recreate the t-shirt movement on the right with the same kind of material, fabric, properties. And we are also able to show that in terms of errors analysis, it works far better compared to all the others. And again, on the left is the input video, on the right is the recovered and estimated material of the same type. Now, you can use this also for garment interpolations of all different type. And as I already mentioned, we actually were able to capture the material as well. We use basically a local and a local patches and a global representation to represent the garment shape. And that also helps us capture all different garment style, as you could see there. The application that we envision and we have applied this to is virtual try-ons. So we have an input video of the dress and we can recreate that dress and we can show you how it on the simulation results. And again, we were able to do this on different body as well. The same kind of silk skirt that you saw earlier, we were able to transfer to this avatar doing karate. And the clothes is all of the same type as the one that was being shown on the left. Okay, so hopefully that kind of give you some idea why such a technology is important. But I do want to say one thing, which I skipped. It's not just about clothing. At the same time, we want to be able to capture the body. Earlier, I showed a single view reconstruction. Even though it does a fairly good job, what we actually did find was we were able to improve the human body reconstruction even better by just using couple more view. So we have proposed a multi-view reconstruction using neural network, a cascading of neural network as being shown here. It's basically a staggered regression block. So we have one view of, could be the same pose, a different pose, and we have 2 or 3 other views. We could have arbitrary view, but what we have found is 2 or 3 view was additional. Two or three extra view was additional would be sufficient and adequate to significantly improve the body reconstruction. So what this does is the input are being treated as images. It goes through and we can extract all the body postures and a parameter is being sent down to this the regression block and refine the poses and the parameter through each block. But we also do share the posture information across. But what's more importantly is because it's the same body. So we do share the body posture both across and also across the same regression block, but also across different view from different perspective, as you could see here. And this reinforces that the reconstructed body is consistent across different view and also different posture. What we have found was the reconstructed body significantly improved on basically body that is outer distributions. So body that are extremely big, extremely small, extremely curvy, extremely skinny, extremely large. Those are the area where we've noticed the most significant differences and did the best across those cases. So here are the input images. On the top row, the middle row is our reconstruction. The bottom was the state of art at that time. You could see that ours does better compared to the state of art. So there are still a lot of really interesting problems along this line. And that is to incorporating differentiable rendering, geometry, and simulation for design pattern recovery, for personalization of customized apparel, for smart fabric designs and 3D printings, and so on. Now, this is some of the work that has been done at Amazon, where we are actually able to also learn the garment draping and prediction for virtual try-on using neural network. And basically, here are the results that that was the draping result that was learned directly from our neural network. And what we were interested is if we have people want to buy t-shirt, they will get a sense of what a small would look like versus a medium versus a large, as you could tell here, so that it can help you shopping on different sizes. I'll let the video do the demonstration. So this is some of the basic example. There has been obviously some earlier work done like TaylorNet, but it does not do as well as what ours can do in terms of reconstruction. And also in terms of, minimizing these artifacts, like the intersections. But this learn dynamics works really well. Works at, better than anything else especially when you have very large body, as we shown here. And again, these are really important cases because these are the customer who have the most problem. It's always the outer distribution body. It's hard to capture its dynamics correctly, and we were able to capture those cases. On just normal distribution body, we do it as well as any other body, any other technique. So the other advantages of being able to learn the dynamics is once you learn the dynamics, you could change the material property on the fly, and you would still be able to get that, the influence done in real time. So in this particular case, we actually imprint different material onto the fabric, and we could see how the fabric actually wrinkles slightly differently, even when it has different material. The material is right here, the trash can print, the graphic print, it's a different material than the t-shirt itself. All right, so, the application of two-tone dresses that I showed you earlier. Here is a replay to show you before and after if you have this technique without versus not having this technique. So you could see the skirt that we have been able to simulate looks so much more realistic with this approach. Now, everything I talk about here not only apply to fabric and bodies and clothing, clothing and pedestrians and traffics and multi-agent systems, but also it applied to multimodal display and interaction. So I just want to show you really quickly. So what you just saw here is a really simple example where we had a single recording. We were able to extract the audio features and then be able to transfer into a real-time interactions of a virtual xylophone. So the user was playing the virtual xylophone in real time, but with the right material, we are able to generate sound synthetically through interaction automatically. And that's what we hope to have moving, going to the future. This virtual synthesis, it's completely possible. You can actually take the real world instrument and bring it to the virtual world, and you can design your own instrument. And here's a perfect example. All right. Sorry. So I want to just say that the audio that you saw here is played by in real time, generated in real time based on user playing. This musical instrument was created in real time on the mobile devices, that small mobile devices. And the material was just basically captured based on the analysis I mentioned. So basically what we're trying to do here is to actually create a framework that we can learn the physical world through this kind of differentiable framework, where the differentiable framework can include the modeling, the rendering, the geometry, and the physics simulation. And it has tremendous implication across vision, languages, and robotics. And the kind of neural network that we can talk about, it could be a convolution network, it could be a transformer, you name it. And we believe this approach that coupled together the learning paradigm with a physical model, where the physical model can be used to jumpstart or won't start a learning process, can be tremendously valuable in terms of reconstruct the physical world and bring it into the metaverse. And we could do this, we have done this through many, many different applications, from learning the physical world. And the physical model that we have, they can serve as inductive biases for the learning algorithm. And we can use the power of deep learning to actually solve all kind of physics problem, as I just demonstrated and shown through a few examples here. All right. I was going to talk a little bit about the differential modeling, but I'm not sure I still have time. I think it ends around 10:45. Is that correct?
It's starting from 10:45. So
Stop it. Okay. I will take question. I'll just end right here by saying, that this kind of approach that I mentioned about reconstructing the reality, there are a tremendous amount of possibility and interesting application. So going forward to the future, I want to say that there are a lot of really interesting problems, which is like transfer learning from sim to sim, sim to real, but also adversarial training of autonomous systems. One of the things we need to also think about is the robustness. How will the robustness affect the corruption and noises as we think about designing physical system, as we think about embodied AI, and as we think about capturing real world. These are some of the work that we have done on new physics, where we combine edible neural geometry with simulation, physics simulation from molecular videos. I won't go into all the detail, but you can see there's just really a tremendous amount of excitement where when we combine model-based approach with learning-based approach to reconstruct the physical world we live in, that will also have the physical property. All right, I'm going to end right here. And just, I think I may have time for one question or two. Any question?
thank you for impressive talks. And any questions or comments? Okay, I have a quick question, Professor Lin. Have you
Okay.
tried
like I mentioned.
okay.
Yeah. Okay.
Have you tried to apply reinforcement learning into the physical to reconstruct reality?
Yes, we have actually applied. We have integrated differentiable physics into reinforcement learning. And we are in the process right now integrating that with the world model to show that we can actually reconstruct the world model a lot faster, an order or two, sometimes three orders magnitude faster. So by integrating the physical model into a learning framework, you could reconstruct the reality a lot faster. We have also looked at the differentiable physics can compute a gradient. We integrate it with reinforcement learning. It's able to do better sampling of the sample and also create better policy. You can also use the gradient to create far better policy and better reward systems. So there's a lot of potential there as well. We have not done all the work. I mean, there are many, many directions to go along that direction. So I encourage people to think about how do we reconstruct reality? And the reality is just huge, right? It's not just about the geometry or the scene, but also about motion, about control of the motion, about manipulations, about embodied AI in the physical world, in the physical system, in the autonomous systems.
Okay, I see. Thank you, Professor Lee. Any questions or comments? Okay, now we thank for the Professor Lin again. Thank
Okay,
you.
thank you.
Let's take a break for 15 minutes.